These are the notes for section 2.3, where we're going to talk about biconditional statements and Venn diagrams. The objectives, these are taken straight from the state. 1B2 says recognize and use the symbols of formal logic, which include these symbols here that I drew. They're not on your notes, so make sure you write those in. 1C1, use Venn diagrams to represent set relationships such as intersection and union. And 1C2, which says to interpret Venn diagrams. The first thing that the notes go over is what a compound statement is. They are statements that can be joined together. Two forms of compound statements are conjunctions and disjunctions. These words are defined right now. A conjunction is joining two or more statements with the word and. The symbol for a conjunction, or and, is a caret sign. The way that I tell people to remember this is it kind of looks like a capital A. So if I would fill this out, that should be easy to remember that that symbol means and. At disjunction, we just flip the symbol upside down. It looks like that, and it represents the word or. Some people will say that you can remember that because some people draw their ors like that, but I think it's just easier to remember the one pointing upwards means and the one pointing downwards means the other thing, or. A biconditional statement is what we're going to talk about next. Is a single true statement that combines a true conditional. So you should remember from our previous notes, a conditional is an if-then statement. So it combines a true conditional and its true converse. Remember, the converse is where you change the order or you just flip it. You can write a biconditional by joining the two parts of each conditional with the phrase if and only if. So we say if P then Q, remember this symbol here means then. That's a conditional, P then Q. This new symbol we learned right here is and. Q then P, which is the converse, is a true statement. So that whole thing is true. Then P, our symbol here is if and only if. This is a new symbol that we're learning. So then the statement P, if and only if Q is true, is a true biconditional. So if and only if is abbreviated IFF, and it is symbolically written as this double-sided, a line with two arrowheads on each side, so just like a line. So remember, in order for a statement to be a biconditional, both the conditional and the converse need to be true. This is going to review some things that we did during section 2.2. Remember, we write a conditional whenever we split the statement on the verb. So the part to the left of the verb is going to be our hypothesis P, and to the right of the verb is going to be the conclusion Q. So the conditional was P then Q. So we have to make congruent angles and if part to fill out the hypothesis. So we're going to say if angles are congruent. So if angles are congruent, you have to be careful with the wording. You can't say if congruent angles, that doesn't make sense. Then, I guess if should also be in black because that's not part of the hypothesis. Remember, everything following the if to the then is the hypothesis. Then the conclusion. They have the same measure. So that's how we change this into a conditional. So let's think about this. If angles are congruent, That means we know that angles are congruent. Do they have the same measure? That is true. So this is true. The conditional is true. And then we have to write the converse. This is where we flip it. So we will say if angles, that's what they represents, angles have the same measure, then, and now we take our original hypothesis, the green part, they are congruent. So is the converse true? So if angles have the same measure, that does mean they are congruent. So that in fact is true. So since both the conditional and the converse are true, we can write a biconditional. So our biconditional will be angles are congruent. So notice I'm not writing an if to start off, because in the middle, I don't write a then, I write if and only if. So if and only if they have the same measure. That's how we write a biconditional. I want you to try this one on your own, number one. I'll get you started though. I will write the conditional for you because I think this is a little bit tricky how to split this up. So again, we find the verb is will, and our conditional always starts with if. So if, you don't say calculators have batteries, I'm sorry, yes you do. You say if calculators have batteries, then they will work. So is this true or false? Well, if calculators have batteries, there's one of two things that can happen with those batteries. It either works or it doesn't. So if a calculator has dead batteries, that's false. So right away, because it's false, the biconditional, there is no biconditional. Remember, both the conditional and converse have to be true. You need to write the converse for this one on your own. The other part of this section talks about Venn diagrams. We talked about Venn diagrams a little bit and how they relate to conditionals in the last section. But the definition we're going to use here are Venn diagrams are used to illustrate relationships between statements and the two words we just learned, conjunctions and disjunctions. So remember, conjunctions dealt with and, disjunctions or. Usually the words all, some, or none, sometimes no, are used with Venn diagrams. So whenever we have something that's all, we would say one set is completely contained within the other. So doing our Venn diagram as before, all bears. So here we go, we have bears are mammals. So this will be completely around bears. So remember, there are other animals that are mammals that are not bears. We can pick dogs, for example. Dogs would be a whole nother thing that's not bears, but they're still mammals. Every bear is a mammal, or all bears are mammals. That's what that looks like. Some, that's one set, is partially, oops, here, is partially in the other set. So if I want to draw this one, it says some football players. So some football players play basketball. So this would be basketball players. And what we're going to have is we're going to have this intersect. Let me change that because I'm not circling the words. So what we would have here is these people here that I'm going to make black, that part in black, those people play both football and basketball. So that's what we mean by some. Those people play both, but then there's people that play only one. The last one is none. The two sets never intersect. The example that's given is there are no oak trees. So we have oak trees in my yard. So out of all the things in my yard, just yard, there's no oak trees. So do you see how they don't intersect? One's not inside the other. That's what we mean by none. We can work the other way where we have to interpret a Venn diagram. This example says use the Venn diagram to fill in the blank with the correct quantifier, all, some, or no or none. So the first one says cloudy days are rainy days. So cloudy days is the whole circle, the big circle. I see that some are rainy days like here, and some are not rainy days like the second X. So I would say some cloudy days are rainy days. Using the other example, part B, it says rainy days are cloudy days. Well, if I'm in rainy days, I'm in this red circle here, which means I'm always in cloudy days. So that would say all rainy days are cloudy days. What I want you to do is try number 2 on your own. Remember, you're just filling it in with all, some, or none. As always, if you have any questions, please ask me, and I hope this was helpful.